the picture you see here, is kind of what we're trying to get to with machine learning in the context of RTPC. So it's an image of a simulation of the full-scale version of what you saw with Matt yesterday, which was the 2x2 detector. That's a prototype for that thing. And you can see there's a very high pileup of interaction going on in there. And so picking out which interaction, or I should say which activity belongs to which interaction in that kind of context is really challenging to do with traditional methods. I was asked to give a brief introduction, so I'll start by addressing why I sound the way I sound. I wasn't born in the land of the free. I was born in Belgium in '91. And I moved out of Belgium basically as soon as I could to do my undergrad and PhD in Geneva. And then after that, I moved to Slack in 2019, and I've been there since, and I'm currently a project scientist over there. My work focus is on machine learning reconstruction for RTPC, so I was hired to essentially put together from the ground up an entirely machine learning-based reconstruction pipeline for RTPCs. And I currently convene machine learning groups at SBN and at DUNE, so that's really what I focus on. My hobbies, I'm basic, so I love hiking and camping, like most physicists you will meet. And I'm also a shade tree mechanic. What that means is that I'm poor, and so I bought a really old car. And in order to just survive at the end of the month, I have to fix it myself. So it's become a hobby for me. So what I have in store for you today is I'm going to be talking about different topics in machine learning. I'm going to first introduce what machine learning is, and then I'll go down different specific architectures that are relevant to doing ML in RTPC, specifically neural network, convolutional neural networks, graphs. Transformers are particularly important in recent years because it's the core architecture at the center of large language models. And then finally, I will mention things that are not neural networks, but are still technically machine learning and in use in DUNE. But it will be kind of a secondary focus for me. And of course, for each of these things, so starting from neural network all the way down to trees, we'll talk about examples of application in the context of DUNE.
Sorry.
Yep. That's okay. Is there? Oh, it doesn't work. I think that's up. Oh, maybe it works.
Oh, sorry. Should work now?
Okay, yeah, that's good. All right, so just to kind of set the stage, you've probably seen this plot before, but artificial intelligence essentially is any algorithm which mimics some kind of human intelligence, and we could have a philosophical conversation about what that means for the next hour, but I'm not going to. And machine learning inscribes itself within artificial intelligence. It's a process of generating an intelligent algorithm from data. That's what machine learning means. So it's a subset of what artificial intelligence is. And then finally, deep learning, which has become particularly relevant in recent years, is yet another subset of machine learning which particularly focuses on artificial neural networks, which are particularly suited for large data sets. And so what ML is, as I mentioned, is turning data into essentially an algorithm. And so if you have a set of data, I'm just taking a basic example here of different people with a certain age and a certain height, and you're trying to predict whether these people are playing basketball or darts, for instance. And so this is just the sample you're looking at. Can you learn by just looking at where these different people fall on this chart, how to find a boundary between the two, and if having some predictive power, just given the age and the height of a person, which kind of sport they're playing. And so these are the different ingredients that go into building an algorithm from the data. So you start with the data set, of course, and then you have an hypothesis set. So that's very important. That's basically what kind of algorithm do you want to fit to your data set, and that's something I'm going to be talking about a lot today. And then you have an objective. The objective is what you're trying to get to. So that's what you want your algorithm to perform. And given all of these things, you feed that into a learning algorithm, which is going to use that target, this objective, to optimize and select a specific algorithm from your hypothesis set. That's what it's doing. And so we're going to go through the different phases that I just discussed. In particular, so an algorithm, which I've been talking about before, is something that maps a set of inputs onto a set of outputs. That's all that it is, right? And the set of candidate algorithms is the set of hypotheses that you can fit to, right? And so it's essentially a parameterization of your problem. So if you think about a polynomial fit, for instance, it's one parameterization of a way to fit some data onto a certain output, right? And so the objective is essentially where we want to get to in that space of the hypothesis set. It's a clear target by which we define whether the model is performing the intended task or not. And in this context, the proximity of the algorithm to the ideal algorithm we're trying to get to is defined as the loss. So it's a measure as to how far the algorithm is from performing the task that we want it to perform. And so the goal of the objective essentially is to find a set of parameters for the hypothesis set that you're considering, which minimizes this loss. So you're trying to minimize the loss with respect to the parameters that you can tune in the model. The objective type, this essentially translates to different training regimens. So there's different things you can train against, and that will define different ways of training the model. And so there's different things you've probably heard about before. So supervised learning typically is when you define your loss with respect to some labels. So it means that you either labeled your data by hand, by just looking at pictures, for instance, and saying what these pictures are, and you train your model against it, or you've run a simulation. So in the context of RTPC, for instance, if you run a simulation and you know the label as to what your detector, what particles were produced in your detector, it is something you can use to train against. And so that's the basic idea, right? So you provide some labeled data to your model, and then you try to have the model predict what is the label given the input without the labels, right? That's all you're trying to do. In the context of unsupervised learning, it's a bit different because now you're looking at data, but you don't have any information as to what you're trying to predict, but you're still trying to infer some information about the data. And so a really typical example of this is clustering. So this is kind of the example I'm showing here. You have a set of data and you're trying to find structure within the data. That's one very specific type of unsupervised learning. And then there's a more recent approach which is called self-supervised learning. So it is supervised, but you don't have to label the data yourself. So that's really nice. And there's different ways to go about doing this. The first way I'm showing is called contrastive learning. And so the way that contrastive learning works is that you take a certain input, so let's say a picture of a cat, and you're trying to distinguish cats from dogs, for instance. And then you modify this picture of the cat, right? So you can translate it around, you can rotate it around, mirror it, you can change the color, etc. And if you do this, you know that the two pictures should be similar, right? So that's kind of a metric you can assign to this training task is, if I'm just modifying a picture, then I should map it to a space where these two things are close to each other, right? And if I now compare cats to another random picture from my data set, they should not be similar by default. And so that's what essentially contrastive learning is doing, is trying to put things together when they are close to each other in the phase space of the data set you're interested in, and put them far away from each other when they belong to separate data sets. Another way to go about doing self-supervised learning is masked learning. And the way you do this is essentially you take an input, and then you mask out part of your input. So if you have a picture, you can match out patches of your input image. Or if you have text, which is particularly relevant to large language models, you can mask specific words inside of a sentence and try to predict what's missing. And so that's the basic idea here. So I'll talk about this again when we get to the large language models. There's also many, many different loss types, and I'm not going to go through everything because that would take a long time. But I'll just give you two really common examples of types of loss you can assign for a certain task. If you have a classification task, so it means you're trying to classify, for instance, an image into different categories. So you could have, pictures of dogs and cats, and you're trying to classify which class each of the pictures belong to. The cross-entropy loss is a very common loss to use, and so you can see here, it is proportional to the true label, that's Y here, and the predicted label, that's the Y hat. And so if your true label is 1, then you want the predicted score, if you want, which ranges from 0 to 1, to be also very close to 1. So if it's close to 1, the log is going to be 0. That's good because your loss is low. But if your score for this given image is close to 0, then your loss explodes because the logarithm of 0, of course, is infinity. And you do the same thing for negative results, right? So if you're trying to say that something is labeled as 0, then you want your score to be close to 0. That's basically what this loss is saying. And then if you have a regression task, what you're trying to do is essentially, for instance, given a particle, trying to reconstruct the energy of the particle is a regression task. And if you do this, there's different types of losses. This is what we call L2 loss, and this is, I forgot a square here. This is the prediction minus the label squared. And an L1 loss is just the absolute value of the difference, right? And Uber loss, just for information, is kind of a mix of the two. So Uber loss will be L2 until a certain boundary, so that's why you see delta equal 1. It's L2 all the way down here, and then it's L1 for the rest of the space. Okay, So now let's talk about the learning process, right? Because I told you how we define a target. I told you what kind of hypothesis set we can define, but how do we actually get to the best hypothesis in that set? And there's different ways to go about doing that. One common way to do this is parameter grid search, right? So you just try everything. Try every possible parameter combination you can try. So if you have a function of 2 parameters, you can just sample within that space a bunch of different combinations of these 2 parameters, compute the loss for each of these parameters, and then pick the one that minimizes the loss, right? So it's kind of a brute force approach. This can work if you're working in a low-dimensional space, but if you have a data set, or I should say a set of hypothesis functions which have thousands or millions of parameters, that's not something you can do, right? You cannot brute force the approach. And so the way we do this is typically to do iterative parameter update. So instead of trying every single point, we start at a random point inside your loss curve, and then you're trying to find the minimum of your loss curve within that landscape. The challenge there, of course, is what path do you take, right? So given this random point you start on the loss, which way do you get to the minimum, right? And so, of course, the minimum is reached when the loss differential is 0, because that's a point where there's a minimum, right? So if you take the differential of the loss with respect to the parameters, and it's 0, then it means that the loss in that region is flat. It doesn't mean that it's a global minimum, but it means that at the very least it is a local minimum. And the way that you get to this minimum is by taking your parameters, which is phi I here, and at the step I plus 1, so it's when you iterate through the parameters of your model, you subtract the gradient of the loss with respect to the parameters. So you're traveling in the direction of the loss being smaller. So if you're at that point here, you can compute the gradient of the loss with respect to the parameters, and it will point in this direction, right? So it points towards lower values of the loss. That's what the gradient is doing. And so that's called gradient descent. And the lambda parameters is essentially a way of defining the learning rate. So it's how quickly you're going to tend to your loss, to the minimum of your loss. So if you set this parameter too small, you're going to take a very long time to converge to the loss. If you set it right, then you will converge quickly and to the true minimum. And if you set it too large, you're just going to bounce around the well, right? So you're not really going to get to the bottom of a loss well in your loss landscape. Okay. I should mention that typically gradient descent is fairly expensive, right? Because you need to look at your entire data set and compute what the loss, or I should say the gradient of the loss with respect to all the parameters is for that entire data set. And so in practice, what we do is stochastic gradient descent. So you take a subsample of your data set, which is a good representation of your entire data set, but with some statistical uncertainty, and you measure the gradient of the loss with respect to that subset. And that subset is what we call a batch. And we evaluate the gradient with respect to that batch instead of the entire data set. And so if you take gradient descent, you can see we tend to the minimum very smoothly because you have less stochastic variation from sample to sample, or I should say from step to step. If you do stochastic gradient descent, you see we still get to the minimum of the loss, which is what we want, but it's a little more jittery, right, because there's more statistical variations. In practice, I should say that stochastic gradient descent is very rarely used these days. It's vanilla method of tending to the minimum, but it has many problems, right? So the issue with stochastic gradient descent is if you have a local minimum, it can get stuck in a local minimum. And that's not something you want, right? You want to tend to the true global minimum of the function. And so people introduce a concept of momentum, and the concept of momentum is essentially if I'm going down a slope, right? I pick up momentum as I go down that slope. And let's say that I hit a little bump on the road. The momentum that I've picked up from going down the slope is something that I can carry into that little bump and just climb over it, right, and keep going. And so there's way more complicated method than what I'm oversimplifying currently to do this. But the point is that currently, one of the most popular minimizer, or I should say methods of stepping through the loss function is called ADAM. So if you want more information, I would recommend looking into that. Now I'm going to talk a little bit about the dataset preparation. So what we assume, that's something I've mentioned before, is that all of the samples you're looking at to train your model are sampled from one underlying distribution, right? And they sample independently from it, which means they're not correlated with each other. That's what we call IID. And what we want is that if we look at new examples of that distribution, that it will be sampled from the same distribution, right? Because we've trained a model on a certain distribution, and we want to apply it to something that looks similar. In practice, there are some challenges with this, right? So if you think about particle physics, for instance, we will very often train a model on a simulation but your data might not look like the simulation at all. And so you might run into a problem where the performance that you get on the simulation is very different from the performance you get on the data. Another problem you can get, of course, that's what we call a domain shift. Another issue we can have is out-of-distribution data. So if you just have very rare realization of your underlying distribution that you've never seen before, how is your model going to behave when it sees it for the first time? That's also something that's quite interesting to think about. And so what we really want to do when we do statistical learning, which is what machine learning is learn the underlying distribution of the data, right? But the problem is that we cannot get to the distribution ever, but we can sample from this distribution, right? That's what we do. So we take a bunch of samples from the distributions. You can think about this as an instance of a simulation of an interaction, a neutrino interaction in the detector. And so the risk, I should say, the definition of risk is the expected value of the loss for that true underlying distribution, which we cannot get to. What we can get to is the loss for a data set, which is a subset of sample from the distribution. So you can take the sum of these losses, and it's kind of an unbiased estimate of what the risk is, but it's not exactly the risk. Right? What I'm trying to get to right now is to tell you that you see this dotted line is the true underlying loss over the distribution of the data set, and the band that you get around it is the variations you can get in the loss landscape, depending which samples you're sampling from the underlying distribution, right? And so if you take this data set 2, for instance, you will see that the minimum is here. If you take the true underlying distribution, the loss is here, and if you take data set 1, the loss is here. So you might get very different answer depending which sample you take from the underlying distribution. And so there's a way to reduce this kind of variation around the true underlying loss distribution, and it is to increase the amount of data you put into your model, of course. And that's why, in recent years, it's been chased after to have very large data set to train a model on. That's what people call big data, because that reduces the statistical variations around the underlying risk. Yes, please.
So I have a question. So when you train on a bigger data set, I know sometimes overfitting can be a problem. So how do you balance those two things of increasing data?
That's an excellent question. That's my next slide. And yeah, so please actually interrupt me anytime you want, and we can discuss any of the things that I'm talking about. If you're confused, please stop me so that, when I get deeper into the topic, you're not too confused. But yeah, I will talk about it. It's an excellent question. Actually, having bigger data reduces overfitting, because when you have smaller data, it's easier to have a model that fits it perfectly, right? But it's a very good question, though. And so how do we, that's exactly what I wanted to get to, how do we get to mitigate the risk for the underlying distribution when we only have one realization of the distribution in the data set that we train on? And we want this to generalize to other data sets, right? That's what we're really trying to get to. And a way to do this is to split the data set. And that's extremely important to know about this, because this is what everybody does, essentially, in machine learning. And you split the data set that you're given from that underlying distribution into 3 pieces. The first piece is called the training set, and that's what we are going to use to train the model on. So that's what the model is going to see to optimize the parameters. And that typically represents a large fraction of your data set, about 80%. Then you have a separate data set, which we call the validation set, which is used to choose the model. So what you can see here at the bottom is the loss curve as a function of training iteration. So I'm training my model, which means I'm updating the parameters of the model as I go. And you can see that the training loss, which is this blue curve, just consistently goes down, which you would expect, right? It keeps getting better as you feed it more and more data. However, you can see that the test set, so the validation set's already lost. So it's the loss that I evaluate on an independent data set, which is sampled from the same distribution, does reach a minimum pretty quickly, and then it starts to increase. And so that point where there's an inflection and the loss landscape for the test set starts to increase is the point where you're starting to overtrain, right? You're starting to fit the training set better than you're fitting the underlying distribution that the training set is sampled from. And so that's where you want to stop. And so that's typically what we do, right? We train, and then we validate, and then we stop where we want to minimize that validation set. And then we have a third set, which is the test set, and that's something we use to evaluate the model performance, because now we've optimized the model given a certain validation data set, and so using that same set to evaluate the performance of the model would be unfair, right? Because that's something you've used to optimize your network. So I hope that makes sense and answers your questions. And so, yeah, you'll see if you ever train a model, which I'm sure you will because it's become ubiquitous in particle physics, it's something you will need to do. Okay, so now I'm going to talk about neural networks specifically. And so the reason I'm talking about neural networks is that I've talked about hypothesis set, and that's basically the set of functions you want to try out to map a certain input onto a certain output. And ideally, what you really want is a universal function approximator. And what that is a function which can map anything onto anything. That's great, because you don't really need to think about it, right? You can stick any input and train a model which will take it to any output you're interested in. So if you can feed it an image, and it will tell you what kind of particle it is or what kind of animal it is, that's something you're interested in, right? And neural networks are great for this. And what neural networks are made out of is these neurons, which you can see here at the bottom left. And this concept was actually introduced in the 60s, so it's extremely old. But it took decades to work because the limitation factor really for neural networks was computation power. So I'll talk about this also later. But the basic unit of a neural network is a neuron which takes a set of input. So you can just think of this as a set of numbers. It could be, position, for instance, in a detector. And then you multiply each of these inputs by a set of weights. So you can think about this as a linear combination of the input. And you add a bias term. So you're just taking, V, which is this linear combination, is the sum of each of the input multiplied by some weights plus some bias terms. It's just a linear combination. So it's a line. You can think about it like that. And then you put that through an activation function. So the activation function is going to be proportional to the input. If your input typically is negative, then it's not going to have a lower response to the input. And if the input is positive, it's going to have a higher response. Yes, please.
Was this algorithm first used to model like neurons?
Yeah, that's a great question. I love that you guys set up my next slide. This is actually loosely based on a biological neuron. I say loosely, but you can think, when you have a neuron, you have a set of input, which are the dendrites. It's essentially what's connected to the nucleus and collects information from other neurons nearby, and then it communicates information to other neurons. So it's really, at least at the structural point of view, looks very similar to what an artificial neuron does. And so, okay, so let's talk about the perceptron again. So as I mentioned, it's a linear model, right? So what it's defining is a hyperplane. I should probably say, it defines a line in a 2D space. But if you have a 3D space, right, then it will define a plane. And if you have 4D space, it will be a hyperplane in 4D, et cetera. But it's basically just a straight boundary between two areas of the space, right? So that's what happens when you take a linear combination of inputs. And then if you put it through an activation function, then it's going to give you different values across that boundary. So if you are above that boundary or below that boundary, so if you're in the negative side of the linear combination, that sigmoid activation function is going to be close to 0. And if you're on the other side of the boundary, this activation function is going to be close to 1. So you can clearly see already how this could be used to do a classification task, right? Because you could say that if you predict the sigmoid function close to 1, then it probably belongs to one class. And if it's close to 0, it probably belongs to the other class. So that's all great, but what if your data looks like this, right? Yes, please.
When you have a ton of different inputs, so let's just say 13, 14 inputs, how do you interpret results like that? Because I imagine it's pretty hard for a human to interpret. It's 14 dimensions per science.
Yeah, it's one of the challenges with machine learning, especially, you say 13, but we get to billions or trillions of parameters at some point. So it's not something I can make a plot out of, but what we can quantify, is how close you get to the objective. So that's what people typically care about, is how well can you actually perform the task that you're interested in doing, rather than really being able to understand what each neuron is doing internally. But it's a very good question. It's one of the challenges with machine learning. So if you look at data set like this, where you have one data set which somehow is made up of two different populations like this, and another data set which is nicely on one line, then you cannot linearly separate these two things, right? So if I put this through a single neuron, I'm not going to be able to find a boundary which clearly separates these two things. And so how do I solve this problem? The way I solve this problem is I just add another neuron, right? So it's pretty simple. The first neuron will create one boundary, and the second neuron will create the second boundary. And now I can use these two boundaries which I've created to transfer the data that I had in my input space into another space of these linear combination, right? And if I do this, the space now looks like this. So here you can see that the axis changed. I had P0 and P1, which are these two input before. And now I have sigma 0 and sigma 1, so it's these two things. And you can see in this new space, where I've transformed the input, these two populations are actually separable, which is what you want, right? And so you can put that through a third neuron, which is now in a second layer, and you can create a linear boundary which will separate these two populations perfectly in that new space. And so you can see where I'm going with this. This is called a multi-layer perceptron, and you can just keep adding more neurons in there. And the more you add neurons in your neural network, the more complex of a task it can perform. And as it turns out, if you make a multi-layer perceptron big enough, it can be a universal function approximator. So it can approximate any kind of function you can think of if you make it big enough. I will say just for jargon that typically the amount of neurons you have per layer in your multi-layer perceptron is typically called width. So here you can see the width of this neural network is 4. And the number of layers you have between the input and the output is called the number of hidden layers or the depths of the neural network. Yeah?
Is there any difference from like adding depth and width, or is it like, is there only?
So there's a lot of hand-wavy arguments about this. It seems like deeper networks typically are a better approach than making wider networks. It depends on specific tasks, but deeper network allow to have higher and higher level information extracted out of your input, because you build upon the previous inputs that you had in the previous network. There were a lot of challenges initially at training these kind of deep networks, because you would struggle to find a set of parameters which work, but it is something that there's been many techniques developed to actually make work, which I'm not going to go into, one of which was residual kind of transformation instead of absolute transformation. But anyway, sorry, this is probably a topic for another time. But it's a good question. So deeper network are typically the preferred option these days. And so yeah, as I mentioned, so if you make your network very deep, then that's what we call deep neural network. So it's a network with a lot of different layers before you get to the output. Okay, and so now I want to talk about optimization of this kind of network a little bit, because as I mentioned before, when we do gradient descent, we need to compute the loss, the differential of the loss with respect to the parameters. And I wanted to discuss how we actually do this in practice in the case of neural networks. So I'm going to do really light calculus with you guys. I hope it's okay. This will be the most math you're going to see in this lecture. But I just wanted to give you a sense as to how we actually optimize the parameters of a network this big. And so we start with a loss. And the loss is a function of the output. So we're just going to take a simple neural network which outputs a single number. And it's a function of the label that you defined as a target for the neural network to learn. And so you can take any of these losses that you can think of. But as you can imagine, computing the loss, for instance, for the L2 loss is pretty simple, right? Because you know the differential of a square. The differential of a square is 2 times the absolute difference. And so computing this loss is trivial. So we don't need to think about that too much. But now you need to think about how do I get the loss with respect to the parameters. I don't care about the loss with respect to the output. What I care about is these things, right? And so the output is, of course, a function of these neuron output from the previous stages multiplied by these weights. So the weights are what I want to get to, right? And then it's passed through an activation function. And so I can just use the chain rule, which means that I can redefine my differential, which is with respect to the parameters here, with respect to the output, and also differentiate the output with respect to the parameters. So I'm simplifying the problem now, because the differential of the loss with respect to the output we know, right? It's the 2 times the difference here, xn minus the label. And then this differential is also fairly easy to compute, right? Because you can look at xn, and the only way it is function of this parameter is through this thing, right? And so that's what I'm doing here. dxn, d phi ni is now this differentiated activation function, which is always known because activation function are always differentiable. That's a choice that we make. And you can evaluate the differentiated function with respect to the linear combination. That's what Vn represents here. And you multiply that by the differential of the linear combination with respect to the parameter phi. And you get, of course, just the value of xn minus 1i. So that's it. So all you need really to compute this difference, this differential with respect to the parameters, is to know the differential of the activation function and to know the value of the output of each of the neurons upstream. So that's all the information you need. It's very easy to do. And if you go even further upstream, then you can just apply more chain rule, and you will get to the differential of each of the loss with respect to each of the parameters upstream. And so you just basically just repeat this process, right? So if you're looking at the differential with respect to this parameter, which is one layer before, then you're now rephrasing it with respect to the output of the last layer, and then the differential of that last layer with respect to that parameter. But that parameter differential is actually only proportional to this parameter here, because that's the only pass to the output, right? And so if you go all the way down, you will see again that the only thing that you care about to be able to compute this differential with respect to the parameter of the neural network is the value of the parameters downstream, the differential of the activation function with respect to the output, and also the output of the neuron itself. And so you've transformed your differential problem into just a tracking problem, right? All the things you need to track are the parameters of the network, the value of the differential of the activation function with respect to its input, and the value of the neuron outputs. And so the reason I'm going through this is to tell you that there's packages to do this for you, and that's pretty important. Because you're transforming the loss gradient computation into a tracking problem where you keep the neuron output and the derivatives of the activation. And so the way that we compute the loss is by going backwards. You start by computing the differential with respect to the last parameter of the neural network, and then you keep going up and up the neural network. That's what's called typically a backward operation or a backpropagation. And automatic differentiation is a tool which keeps up with all this information for you, and that's something that multiple different packages do, and Matt talked about this yesterday. PyTorch and TensorFlow are the most popular two packages to do automatic differentiation. And in the next session, I will talk about PyTorch a lot. So PyTorch is the most popular automatic differentiation package for neural networks, and that will be the tool for later today's session. Okay, now I want to give you a brief example as to what we can do with a basic neural network. And for this, I will take the example of light propagation in liquid argon time projection chamber. I'm assuming because you were here this week that you're now expert about time projection chamber, LRTPCs. But I'll remind you that when there's a particle going through your detector, it produces charge, which is drifted towards the wire planes here, so that's something you can collect. But it also produces light. And light is collected by these light collection system. For instance, photon multipliers, tubes. And so what we're really interested in is to try to know how much light we expect to see when you run a simulation, given the amount of charge deposited in the detector, right? So it's kind of a light propagation understanding. And it turns out that doing this kind of simulation is extremely expensive, right? So if you had to simulate each individual photon and how it propagates into the liquid argon, this is something that would take hours, and you would never be able to produce a simulation data set. And so the way we do it is we still do the simulation, but we only do it once. So we simulate a bunch of photons in a bunch of different pixels inside of the detector. So you voxelize the detector, right? You divide it out in a lot of different bins. And for each bin, you generate a bunch of different photons. And for each of the light collection system, you measure the amount of photon that you collected in that light collection system. And that gives you a visibility map, right? So it tells you the probability that given a photon generated at a certain point, will it or will it not produce a signal onto my light collection system, right? And so the challenge with this method is that you make very, very large maps. So if you think about Icarus, for instance, the number of parameters that you need to put into your model is proportional to the number of light collection systems you have times the volume of your detector divided by the size of your voxel, right? So it's the little bin that you are producing light on. If you do this for Icarus, it's a very large liquid argon time projection chamber. It's the current largest time projection chamber. That takes about 404 megabytes. So that's something you have to put in memory when you're using that lookup table. If you scale that to the far detector of DUNE, which is significantly bigger and has more light collection system, that is something like 100 gigabytes, right? So if you have to put that in memory, that's really a fundamental problem. So either you don't put it in memory, but then you pay the cost of having to look up inside a file each time, or you put it in memory and then you have some serious limitation as to what kind of hardware you can use. And so a solution to this is to use a multi-layer perceptron, right? And so that's what Siren is. Siren is essentially just an MLP, which takes as an input the position of where the light was produced in the detector, and as an output gives you the visibility value for each of the photon collection system in your detector. There is one very special thing about that model, and it is that the activation function is not a standard, smooth activation function going from 0 to 1. It is a sinusoidal activation function, so it's just a sine, right? And that's quite particular. And the reason we do this is that when you're trying to encode an image, which can have really sharp rises in certain places and smooth rises in other places, a Fourier transform is a really good way to do this. And the Fourier series is just a sum of a bunch of sines, right? And so this is what the neural network is learning to do. It's just learning to encode the image into a bunch of sines, which I don't know if you know, but this is what the JPEG format does. So JPEG format just converts the value of each of individual pixel in your image into just a bunch of sums of sines inside your image. And so that's what the network is doing here. And we start with the data set of using the lookup table. So we use the lookup table we produced with the simulation, and we train the model to reproduce the lookup table. So if you do this, you'll see that you can reproduce the lookup table very well. So this is just a picture of what the lookup table will look like if you sum the visibility of the photons for all of the different light collection system in Icarus. And this is what you get if you do the same by encoding that information into a neural network. What's interesting to know is that Siren only has 1.5 million parameters, so that's 1.5 megabytes. You can think about it like that, it's not quite. But if you look at the lookup table, that's 300 times more parameters. So you've encoded the same amount of information into a lot less parameters, which is good, because it's about to learn greater structures instead of just trying to encode it pixel by pixel. Here on this right plot, you can see the visibility predicted by Siren as a function of the visibility observed in the lookup table, and you can see that there's a very nice linear correlation between the two. We can actually do you one better with Siren, and it is to actually learn the light propagation by just looking at data, which is very cool. This is not something you could be doing with the lookup table, but the way we proceed is that now, instead of using the lookup table to train, we use pairs of track interaction in the detector and the light signal that we see in the light system. So you just take a very controlled sample of single muons crossing your detector, you record the amount of charge deposited in your detector in what places, and you also record the amount of light that you see in each of the light detector, right? So this is what these plots are showing. This is the amount of light collected in each channel. So each channel corresponds to one light detector. And then what we can do is we put the charge that we have deposited in the detector through the neural network, and we produce an output as to how much light we expect to see, right? And you can compare this to the amount of light that you actually observed in your detector, and you can optimize the neural network parameters this way. And so by doing this, you're learning the light propagation system directly by looking how the light propagates in your detector instead of relying on simulation, which is significantly better. And the reason it's significantly better is that if you just use the lookup table as it is, this shows you the agreement between the amount of observed light minus the amount of predicted light that you get when you look at your actual data, and you can see that there's a substantial disagreement between the two. But if you train the model directly on the data, you can see that these two things agree to a much greater degree. You can see a disagreement on average of about 4% with respect to 10+%. And so not only can you not rely on simulation for producing your light propagation system, but you also get a better approximation to what you actually will observe in the data. So that's quite cool. I'll also briefly mention how you optimize hyperparameters of the network. So you were asking me about how many layers should you put into your neural network, for instance. And so the way that we do this is just by trying a bunch of different things and seeing what works best, right? And so here you can see the number of layers in the neural network. So that's the amount of hidden layers between the input and the output of the neural network. And you can see the number of features. So that's the width, right, of your model. That's the number of neurons that you have at each layer. And you can see that there's a relatively strong correlation to the width, right? So if you start with a small width for your neural network, the performance is quite poor. As you go to higher widths, the performance improves. you can see that there's not much improvement between 64 and 128. And what's also interesting to see is that there doesn't seem to be much improvement by adding more layers. So in this particular case, when you're encoding this basic function, it makes sense to go to a low number of layers and a very high number of features. So that's what we ended up doing. Single layer, 128 neurons. So it's a very small, compact, and basic neural network to do this task. Okay, I'm going to talk about convolutional neural network. And this is particularly relevant because CNNs are great at image processing. And image processing is what we want to do when it comes to liquid argon time projection chamber. Because as you know, these detectors are essentially cameras taking really detailed particle pictures like this. And so it's just a bunch of information about where there was charge deposition in the detector and at what intensity, which is essentially a picture. And so if you could process these things that get information out, that's really what we should be doing. Okay, so I have to use cats because it's a machine learning talk. And I'm going to ask, can we use a neural network to process image data? And one way you can do this is you just say, okay, I'm going to take each pixel in my input, and I'm going to flatten the input. So I'm just going to make that a really long vector, right? So each pixel in the input is going to be one number in a very long vector that I put into my neural network. And then I can use a multi-layer perceptron and get the output that I want. So I can get scores, essentially, for each of the different classes that I'm trying to get to. This is likely to be a cat, this is likely to be a dog, etc. The challenge with this approach is that you have a boatload of parameters. Because if you just take a simple image, which is just 100 by 100, that's already 10,000 pixels, right? And then if you have an RGB channel, so it means you have red, blue, and green channels for the image, then that means you multiply that by 3, and so you have 30,000, yeah.
How could you, like, for example, since like so much of the background is just white, right? It's just a plain background. Can it possibly bias the background? If that makes sense, like, so if you had a horse that had a white background,
yeah.
Because it had a white background, that was similar to the cat data you trained on. Did that happen?
Yeah, I mean, certainly, I mean, if you have a correlation between two features, it can certainly learn that there's a correlation between the features. So it's a good point. If every single horse was on a white background, and you suddenly had one cat on a white background while all other cats were red, this is something that's going to be a problem for a neural network to learn. But yeah, to get back to the complexity argument, the issue is if you have an input vector of 30,000 parameters, then if you connect all of these to a single neuron in the second layer, you already have 30,000 parameters in your neural network. And so as you add more intermediate neuron here, the amount of parameters you have to deal with actually explodes. The other issue you have is that it's not translational invariant. So what this means is that if you're trying to extract features from a tail of a cat, for instance, and you just move that tail somewhere else in the picture, then the response of the neural network does not have to be anywhere close to the response to the other image, even though they are essentially the same picture, just shifted, right? And the reason for this is that if you flatten the input, then if you move the tail, it's going to be connected to different neurons downstream, right? And so it's going to respond differently. So how do we address the issue? The way we do this is by doing convolutions instead. The way that works is that instead of having a neuron connected to every single input in the image, you restrict the receptive field of the neuron. What that means is that the amount of input it takes in is actually restricted to the neighborhood of a pixel you're interested in. So if you're doing a convolution on this red pixel in the input, then the only things that will be connected to the neuron, the hidden neuron, to produce a new set of features is the pixels within some vicinity of the pixel that you're pushing through the neuron, right? And doing this is what's called a convolution. I'll get back to that in the next slide. And it's still a linear transformation. So we haven't really changed the fundamental core principle of a neural network. We've just restricted the information that goes into updating the features of the next layer. What's also really important to point out with respect to a multi-layer perceptron is that the neuron is actually shared across the entire image. So you don't have different neurons doing different convolution on each pixel. You have a single neuron which slides over the image. And so it's going to be convolved with the entire image progressively. In practice, this is what it looks like. So if you take a convolution kernel, so this is what you see on the left, you have a bunch of different values. These are essentially the neural network weights that we're trying to optimize. And you take this kernel and you just slide it over your input image, right? So it's going to start here in the top left corner, and then it's just going to slide over to the next one, and then keep moving down until you've processed the entire image. And what the way that the output is produced is by taking the sum of that kernel with all the values in that neighborhood of the image, right? So if you do 1 times 1 plus 0 times 1 plus 1 times 1, etc., you will get the number 4. And then when you've moved it to the next number, then you do 1 times 1 plus 0 times 1, etc., and you get the number 3. And that's how you update the features, the feature map corresponding to the input image. I hope that makes sense. Great. So I'll keep going. Now, how can we use this convolution principle to actually do image classification, which is the most basic thing you can do with a CNN? And the way you do that is just by doing what I explained on the previous slide, which is you take a certain region inside of the cat image here, and you convolve it with a 3x3 kernel, for instance, so you can have different sizes of kernel for different tasks. And what you get is a new set of convolve feature in a new image. And if you repeat this for the entire input image, then you get a feature map for that image, right? So you've updated the information that's associated with each pixel inside the image. That's what the convolution is doing. If you do this with a bunch of different neurons, which you can, right, multiple convolution kernels, then you get an n-fold feature map. So it means you get information extracted by different neurons, which might focus on different things in the image, right? Then what you can do is you can downsample. The way that downsampling works is there's different ways to do this, but one of which is to do pooling. So you take information from a small region in the image and you add it together, for instance. That's one way to do it. Or you can take the max. So for instance, if you have a 4x4 image, you can divide it in regions of 2x2. That's what's called pooling, 2x2 pooling. And you can either take the max of the sum or some kind of summary statistic of these numbers and produce a new image with it. So if you take the max, for instance, and you take this region, you're going to put 6 out. If you take this region, you're going to put 8 out, etc. And what this does is effectively reduce the size of the image, right? Because you're combining 4 pixels into one. And so if you have a 100 by 100 pixel image, you're going to go down to a 50 by 50 pixel image, right? And the interest of doing that is that you can actually extract features at different scales of the image, right? Because if you have a 3x3 kernel, it's going to focus on a small neighborhood around the pixel that you're updating the features for. But if you go down by a factor 2, then you're now looking at an area of 6x6, right, but with a 3x3 kernel. And so by repeating this process many, many times, you can extract features at many different scales of the image. Once you've done that, so you've actually compressed the image all the way down to a single pixel, then what you're left with is just a really long array of features, right? Because it's a single pixel with a bunch of features associated with it. And what you can do with that one dimensional array is put it through a neural network, this time through an MLP. And at the end of the MLP, you can ask, is this a cat or a dog, right? So it's just going to be a logistic prediction between 0 and 1, for instance. And this is all a neural network, all the way down. And so we can compute the loss with respect to all the parameters that go into this. And we can update the values that go into these convolutional kernels, given the loss that we've computed at the end. Okay, and so is this used in LRTPC? Well, of course it is. The first way that it was used actually was in the DUNE CVN, which was developed a long time ago now. And the basic idea was you take the 3 images that you get out of your detector. So if you remember, the 3 different wire collection plane in most liquid argon time projection chamber. And so each of those produce one 2D projection of what happened in your detector. And so each of which you can put through a convolutional neural network like this one, right? And so each of these will give you one vector like this, right? So you've put 3 different images through a CNN, each of which have given you one of these. And then you can just stack these 3 things together into an even longer vector, put it through, again, here, another neural network, and then you can get a bunch of different outputs. So you can get the type of neutrino interaction, you can get the type of, the number of protons, for instance, that came out, whether it's a neutrino, an anti-neutrino, et cetera. So a bunch of different classification output. And this turns out it works pretty well. So if you do this on the fall detector simulation, the black curves essentially show you what we were. The black curve essentially shows you the efficiency at identifying a neutrino interaction correctly, given the energy of the neutrino interaction. The dotted line is kind of what we were trying to get to, right? So it's the target performance that we want for the DUNE fall detector. And you can see that it's not too far off. This is on the left for electron neutrino, and it's for muon neutrino on the right. Another thing you can do with CNN is segmentation. So it's a bit different now. You're not trying to classify the entire image as one category. You're trying to identify which of the pixels in the image actually belong to a certain class. So you're saying, tell me every single pixel in the image which belongs to a cat. That's a more specific thing to do. And this is slightly more complicated, but the basic idea is similar. So you still start with the same kind of neural network that I talked about before, where you're doing progressive convolution to reduce the size of the image and extract information at different scales. But the difference here is that you add another site to this neural network, which goes back up in size. So you want to go back up to the original image size because you want to make inference about each of the pixels in the image that you started with, right? And the way that we do this is by doing transpose convolution, and transpose convolution convolve individual numbers in an image with a kernel, which is bigger than a single number. And what you get as an output is more numbers, right? Because you took a single number that you multiplied by a kernel. And so effectively, you're increasing the size of the image by doing this kind of transpose convolution. So that allows you to go back up the size all the way back to the original size. The issue here with this architecture, which is called an autoencoder, is that you need to learn to encode the entire input image to reproduce it on the other side. But we don't need to do this, right? We're not trying to encode the input image. We're just trying to make prediction about individual pixels in the input image. And so we add skip connections. So these skip connections essentially allow the neural network to retain the detailed information about what the image looks like, but it still allows it to also extract information about the individual pixels in the image. So you get these two different features combined together into one. This is called the DUNE-TECH, and it was first developed for cancer segmentation in 2015, and it's been an incredibly popular neural network architecture since. And in fact, it's still used to this day. This is something from a reconstruction package that I work on, where we try to classify each of the different energy deposition inside of the detector into different particle classes. So you start with a bunch of energy deposition you know nothing about, and what you're trying to infer is what kind of particle interacted in the detector. So if it's a muon, a proton, or a pion, for instance, you call that a track because it looks like a rectilinear object in your detector. And so you're trying to say which of these depositions actually belong to track particles and which of these depositions belong to electromagnetic showers, for instance. So when you have an electron or a photon interacting in the detector, it's going to create a bunch of different fragments in your detector, and that's called an electromagnetic shower. And you can see it did a pretty good job at saying, oh, these two things are electromagnetic showers, and all of these points belong to tracks. It also identified this Michel decay, so it's when a muon comes to a stop and decays to an electron. You can see that that belongs to a separate class. And then you also have delta rays, so it's when a particle is traveling through your detector and it just knocks out an electron which travels relatively parallel to a track that's called a delta ray. And you can see one of those right here, for instance. This is a confusion matrix. So I'm not sure if you've seen these before, but you're going to see a lot of those later today, which essentially tells you how accurately you're doing your classification task, right? So on the bottom row here, you have the class label. So that's what you're trying to predict. So if you have a certain pixel, it is labeled either shower, track, Michel, delta, or LED. And on the y-axis, this is what your neural network put out, right? And so if you are on the diagonal, you're happy because it means you did a good job. You had a shower pixel and you predicted it as a shower pixel. If you're off diagonal, it means you made a mistake and you predicted it as something else. So you can see, for instance, that the shower track separation is very, very good. The track accuracy is at 99.5%. The shower accuracy is at 97.9%. And the probability of predicting a shower pixel as a track is smaller than 1%. Right? This is what this is telling you, 0.6%. And conversely, track to shower is smaller than 1% at 0.2. And so you can see that for smaller class, the challenge is a bit harder. So for instance, there's some confusion between delta and track. And the reason for that is delta and track are always on top of each other, right? So finding the exact boundary between the track and the delta is something that can be quite challenging. Okay, now let's talk about graph neural networks, which is another class of neural networks. So CNNs, which we just talked about, state of the art for computer vision, but they have some limitation, right? So one is that the data must be on a grid. And so one thing you can do if the data is not exactly on a grid is you can force it down on a grid. So if you have the deposition from an RTPC, for instance, they're not necessarily on a grid, but you can certainly collapse them onto a grid. That's what's called rasterization. And they're also not extremely good at finding really far-range correlation. So if you have two objects in an image which are very far from each other spatially, it's very difficult to find information about how they are correlated with each other. And so for that kind of data, or I should say, this is another couple of examples of what kind of data might not be represented by a grid. Social networks, for instance, of course, there's no sense of spatial position, and so you cannot represent that with an image. And also paper references, so it's how paper reference each other on the archive is something that's a data set that can be represented by a graph. So what is a graph? Well, a graph is pretty simple. It's just a set of three things. It's a set of nodes. So each node is a piece of information that you're putting to your neural network. Edges are connection between these nodes, so the connection between these pieces of information. So you can think about a node as being a person in a social network, for instance, and the edges as being relationship between these people. So if there's no connection between two persons, you have no edge in your graph. But if they are a friend, then maybe there's a connection within that social network. And then the global state is information about the graph as a whole. So if you look at the entire graph and you characterize it by a set of information, for instance, the type of social network, it might be a work social network, it might be a friendship social network. This will be encoded in the global state of the graph. There's different tasks you can perform with a graph. There's node level task where you're trying to classify each of the nodes as belonging to a specific class. And I'm giving you one such example. So this is a pretty typical example in graph theory, where you have a karate club of people which are all in one club. And at some point, there is a falling out between two of the senseis in the club. And they just part ways, right? So one starts this new club. And the question you're asking is, what is the probability of a certain person within the original club to go with one person or the other, right? And so what these edges represent is friendship within the club. And what you're trying to predict is whether a node is going to go with A or with I when the club splits. So that's a typical kind of node type of task that you can do with a graph. There's also edge tasks. So you have information, for instance, about a social network. So you have a bunch of different people. You have information about each of these people. So that's kind of the node features. And then you have a bunch of potential connection between the people in the social network. And what the task could be is to try to identify how these people are connected to each other without any prior knowledge about whether or not they are connected with each other. But maybe their habits, where they go to eat food, etc., might hint at the fact that they know each other. And then for an entire global task, for an entire graph, one typical example is enzymes. So enzyme is a data set where enzymes, which are proteins, are represented as a graph. So each amino acid in the enzyme is represented as a node in the graph, and then the connection between the nodes in the graph represents some kind of bond between the amino acid within that protein. And something you can ask is, what is the function of that protein given that graph? So I know the set of amino acid, I know how they are connected to each other in the enzyme. What is the purpose of this enzyme in the body? It's something you could try to classify. Okay, now I want to talk about graph convolution, and I want to relate that to CNNs, essentially. So how do you pass information through a graph, right? Because in a CNN, it's pretty obvious you take a neighborhood of around a pixel, but around a graph, there's no neighborhood defined by proximity anymore. And so the way you do this is by defining proximity by connection with other nodes in the graph, right? So you're just making something more general than a CNN, where the receptive field is no longer defined by what's close to a pixel in the input image, but it is defined by what edges you give to the graph, right? That's what's called an adjacency matrix. So if you have two nodes in the graph A and B which are connected by an edge, then in your adjacency matrix, you will have the number 1 here. And if you have two nodes which are not connected, so you take B and D, for instance, B and D, then the value of the adjacency matrix here is 0 because these two nodes are not connected with each other, right? And so in images, you would take a kernel and you would convolve it with the input pixels. In a graph convolution, it's a bit different because now you're only convolving information when there is a connection between the two. That's basically what this adjacency matrix is doing here. And that the degree here is dividing by the amount of connection that goes to a node. Because if you have a node connected to 10 other nodes, it's going to get more features to it than if it's connected to one. But you don't want it to scale with the amount of connections. You don't want. So the way that you handle this is by using degree. So if you have a node connected to 10, you're going to divide the convolution output by 10. If you have only one connection, then you just divide it by 1. And so this is what it looks like. You're just progressively convolving information from nodes that are connected to the node that you're updating as you go through each layer. So it's a bit like a CNN where you're convolving with a single kernel at each stage, but this time you're convolving with respect to the neighborhood in the graph, which is defined by these edges. This is called a graph convolutional network, or GCNs. The issue with these networks is that they are pretty limited. So they're node focused, which means you only look at node features. There's no information about the edges, for instance. So if you want to encode some information about this edge is a friendship, this edge is 2 colleagues or something like that, that is not something you can do with GCNs. Also, the way that the neighborhood aggregation is done is by just taking the sum of the features and dividing by the amount of connection. And that's something you might want to do something different for, right? You might want to take the max feature coming from the neighborhood instead of taking the mean. And also, they are undirected and unweighted adjacency. So that means you cannot give more weight to certain connections than you would other connections. And so there's a more general formulation, which is called graph neural network, which uses the concept of message passing. And the way message passing works is you have progressive update inside of your graph in 3 different stages. The way you start is by updating the features that are associated with an edge. So you have information about an edge to start with, right? That's what this is. And then you combine it with information from the node. So if you have an edge here connecting these 2 nodes, you can take the features from the 2 nodes and the edge, and also the global state of the graph, which is this U here, and put that through a neural network. That's going to effectively change the input edges into a new set of features for that edge. That's what's called edge update. Then you do the same, oh, there it is. Then you do the same for the nodes. In this case, for the node, you take the features of the node before the update, that's what this is. You take an aggregate version of what information is coming from the edges, and this aggregation function can be anything you want. So it can be a max, it can be mean, it can be sum. You're just taking information from all of the edges connected to that node, and you're aggregating in some way to make it a single vector, right? And you're also taking the global state of the graph, of course, into account, and that allows you to update the node features themselves. And then you do the same, finally, for the global state of the graph, where you take an aggregation of all the edge information, all the node information, and the current global state to update it. Each of these functions that you see here, phi, e, v, and u, are 3 different neural networks, typically just MLPs, so multi-layer perceptron, which we talked about before. And this is the most generic definition of how you can put a graph together. I'm just giving you an example as to how information propagates now inside of the graph. So you see, if you start with the information from this node, and you haven't done any message passing yet, then only this node is aware of the information that's coming from it. After one message passing task, you can see that the information is now propagated to the 3 nodes that it is connected to. You can see the same thing here. This node has propagated information here. With the second step of message passing, the information from this original node now has traveled the entire graph. So all of the nodes in the graph actually have the information from that node that we started with. And at the end, you see we've covered everything on the top, but on the bottom, there are some nodes that we cannot reach, right? Because we started here, and there's only directional edges from this node to other nodes. So this node just does not receive information from other nodes, which is quite particular. Okay, so now I'm going to give an example, again, in the context of RTPC, which is more relevant than the example I gave earlier, where we start with a bunch of different fragments in the detector. So this is electromagnetic shower, which I talked about before. And each electromagnetic shower is made up of a bunch of different particles, right? So each of these small particles you see is an electron or a positron in the detector traveling, or a combination of such. And what you're trying to do is combine these different fragments together into one instance if they originate from one primary electron or photon. So when you have an electron going in through your detector, it's going to emit photons, which are themselves going to produce electron and positron. And so everything here, for instance, originates from one common ancestor, but they're all separated in the detector. What you're trying to do is find correlations between them. You cannot do this trivially with a CNN, but a GNN is a really great way to do this. So this is the group you're trying to build, right? I'm just giving you the answer. And the way you can formulate this task is, please, neural network, tell me which of these connections is actually relevant to put these things together. So if two fragments belong to the same instance, I want the graph neural network to tell me that this edge is connected, right? And so you can do different things. So this is the Icarus detector, which is a very big detector. It's about 20 meters long, 3 by 3 meters in cross-section. So you can connect all of the fragments together in the image, right, and say just sort it out. That's one way to do it, and actually works okay. The issue is, of course, computationally, you're spending a lot of time dealing with a lot of edges which are unphysical, right? Because if you have an electromagnetic shower starting here, it's impossible for it to be connected to a fragment living over there. And so you can use physics principle to restrict the graph that you build on the input nodes. And for instance, you might know that a photon in the liquid argon, a bath, will travel something like 20 centimeters before it interacts. That's the mean free path. And so if you take a cut at like 150 centimeters, 1.5 meter, then you can be pretty certain that a photon did not travel that far, okay? And so the graph that you build looks something like this. And now this is the edges you have to sort through instead of the mess that you see on top. And so now we need to build a graph, right? So we need to somehow convert the set of fragments that we had